recording the lectures. I already shared the screen and thing. So now, before going into this course, so what is a signal? What is a signal? Signal is an information variable represented by physical quantity. What are different physical quantities? What are different physical quantities? Voltage is a physical quantity. Okay. Pressure is a physical quantity. Temperature is a physical quantity. So signal is an information variable which represent a physical quantity. So okay, for digital system, the variable take on discrete values. What are these discrete values? There are only two levels. Two levels are used, okay? Or binary values are the most prevalent values in digital systems. And what are these values? I will explain this with an example. So binary values are abstractly represented by digit 0 or 1. Then true or false. We can also say low or high, off or on. Okay, now let's assume you're sitting, and I'm standing. So it represents one value, it represents other value. Okay, so logical 1 and logical 0, on and off. Okay, and low or high. So these are binary values are represented by values or range of values of physical quantities. Now, if you consider this time, time is a variable. Time is a variable. Okay, now if you look at this time, red line, this is continuous or discrete? It's continuous. Okay, because we have this time, this is all these continuous. But if we say, and these are discrete time instant at regular intervals. So and the green thingy, continuous or discrete? Discrete. So these are discrete. So in the black, the time is continuous, and in the red, the time is discrete. Okay, so red is discrete, black is continuous. Now we have a signal. This is an analog signal. Now we have two different things. One is the timeline. This is the timeline, and now this is your signal. And it can be any quantity of interest. It can be a temperature. It can be a pressure. So if we say, now this is our signal. Maybe this is the temperature over time. Maybe this is the temperature over time. So maybe we have something. So what is the range of temperature from? Let's assume from 0 to 50 degrees centigrade. This is maybe the temperature over time. Okay. Now we have a value. So the value is continuous or discrete? The value. This is the value. Continuous or discrete? Continuous. So the value is also continuous. And what about time? Time is also continuous. So the value is also continuous. Value is on the y-axis. Time. The value is also continuous, and the time is also continuous. Okay. Now we have a digital signal. It takes on two values. Remember, what are these two values? On, off, low, high, blah, blah, blah. So now if you look at here, so now we have a high value, then we have a low, then high. It takes on only two possible values. It takes on two possible values, high and low, off and on. Got it? So now the value is discrete or continuous? The value is discrete. What about time? Time is continuous. Got it? Now, discrete in value and continuous in time. Now, if you look at this signal, okay, now we have discrete time instances. What are discrete time instances? Can you see here? T0, T1, T2, and T3. Okay, now if you look at this signal, which is called a synchronous signal, which is discrete in value and time, because this signal is only changing at time what? T0, then T1, T2, and T3. Okay, it's not changed. Okay, that's one, it's still one. It doesn't change. It doesn't matter that it's changed. So, but the signal can only change a discrete time instant. This signal is called as synchronous signal, which is discrete in value. What is discrete in value? 0, 1, 0, 1, and 1. And also discrete at time. It can only change at T0, but if you look at the asynchronous signal, it does not, it can change at any time. You got it? Any question? Should we proceed? Okay. So now these are the notions. Now, What about the if you take off about two quantities like binary 0 and a binary 1, so we can represent it with the voltage. We have a voltage. Okay, now if you look at the voltage, what is the maximum voltage that we have? 5 volt. What is the minimum volt? 0 volt. So we have range. So if we say if the voltage is between 0 to 1 volt, what does it imply? 0, and it means 1. And in between it's called as indeterminate. Neither a logical 1 nor a logical 0. It can be used to represent a logical 0, and it is used to represent a logical 1. Similarly, if you have the output, what is the output range from 0 to 2? Logical 0, then logical 1. In between, indeterminate. Okay, now I'll explain this with an example. This is a chair. I'm sitting. Logical 0. I'm standing. Logical 1. Okay, now, but what about this? No, not indeterminate. Maybe I'm close to sitting, maybe 0. And like let's assume I'm like here, I'm close to 1. This card is logical 1. So it means that you round it off. So if the voltage is 4.2 volt, it will consider it as a logical 1. If it is 0.2 volt, logical 0. But if it's 2 volt, indeterminate, and there will be an error in the system. Same thing for the output. If it's between 0 to 2, 0, let's 1.5, logical 0, 4.2, logical 1, 2.5, indeterminate. Neither a logical 0 nor a logical 1. So now we have two discrete values. And how do we represent these discrete values? Okay, now we have what are other physical quantity which represent zeros or 1. So if we talk in terms of CPU, so we can talk in terms of voltage. So in the previous example, the voltage was 0 volt and 5 volt. 0 volt was representing a logical 0, and 5 volt was representing a logical 1. So we say high, the voltage can either be high or low. So we can represent the discrete quantities. And now disk, if you store the data in a disk, so the data can be now represented in the form of magnetic orientation. I will explain this with an example. So now let's assume if it's from north to south, it can be used to represent a logical 1, and from south to north, logical 0. And okay, now if it's something like this, still a logical 1. And if something like this, still a logical 0. Got it? So now the data can also be represented in the form of the magnetic orientation. One direction will represent a logical 1, other direction will represent a logical 0. Similarly, we have CD-ROM. In CD-ROM, so in CD-ROM we read the data or write the data. So we store the data in the form of land and bits. Let's assume if we strike a light, okay, and then the light returns back. So it's transparent or opaque? Reflecting, opaque. Okay, and if it passes through, transparent. So one can be used to store a logical 1, and other can be used to store a logical 0. So there are two states. One is opaque and one is transparent. So opaque can be used to represent a logical 1, and transparent can be used to represent a logical 0. Or in the form of we also store the data in memory. In memory, we store the data in the form of an electric charge. So we store the data in the form of a capacitor. So there are two possibilities. You may have studied in your 12th grade. So either the capacitor can be charged or discharged. If capacitor is charged, it can be used to represent a logical 1, and if it discharged, it can be used to represent a logical 0. Now we have a bulb. Bulb is on, bulb is off. One can be used to represent a logical 1, and other can be used vice versa, and a logical 0. And let's assume I'm sitting and I'm standing. So I'm sitting, it can be used to represent a logical 0, and I'm standing, it can be used to represent a logical 1. So what are the numbers? So computer only understand numbers, and numbers are very important to computers. So now if you say number represent information precisely, and it can be processed. I will explain with an example. Okay, now to represent yes or no, you can say 0 for no, 1 for yes. Then to represent 4 season, computer doesn't understand season. It doesn't understand season. So you can say we can give different coding to different seasons. So you can say, okay, what is the code for autumn? 0. What is the code for winter? 1, 2, and 3. And you may change the coding. It's not you may assign 0 to summer and 1 and 2 and 3. It's up to you. Then the computer should understand. So whenever the computer reads 0 in this particular example, what do you interpret? Autumn. So numbers are important. Okay, so represent 4 seasons, you have different representation on number. And now, if we want to represent 7 colors of the rainbow, which is called as Vibear, so violet, indigo, and we have different codes for different. So what's the code for violet? 0. So it's with 7. What did it mean? Right? The second thing is something. Okay. Now Emirates ID. Now you have an Emirates ID. You have a 15 digits to represent an individual in UAE. You can have 15 different digits. Okay, and it can be an array of characters. Similarly, in AUS ID, you have some characters. It can be stored in some form of characters. And you also know in your computer programming course, you also have the ASCII representative. Remember? So these are characters, but these characters are also transformed into some numbers. So what is the ASCII code for A? What is the ASCII code? Yes, for 197, 165. So capital is 65 and small is 97. So they are also represented by numbers. So if you print an A, so in computer will interpret it as 65 because it's transformed into number. So numbers are important to computer. So we will also deal with all of these numbers in our today's lecture. What are different representation of different numbers and how numbers will look like, we will see it. Okay, if I'm doing too fast, please interrupt me. If you do not, you can interrupt me. So what's a number system? So a number system, how a number can be represented by using different distinct symbols. So now we have the number an minus 1, an minus 0, a1, a0 consists of n distinct symbol where an minus 1 has the highest weight and a0 has the lowest weight. I will explain this way in example. So the commonly number used system are the decimal numbers. The decimal number, which is understandable by whom? By humans. Each symbol can have 10 possible values. Digits can have value from 0 to 9, which is also called as base 10. And this is called an example. So, okay, now if you look at here, so now we have 9, 5, 6, 9, 5, 6, and 10. So the numbers start from what? An minus 1. Okay, so what is n here? 3. We have 3 digits. What is the base? This is your base. It starts from an minus 1. So an minus 1, a2, then a1, a0. Which one has the highest weight? A2 has the highest weight. An minus 1 has the highest weight. So the same thing. So 3, 4, 9, 7, 8. This is what? A4, A3, A2, A1, and A0. And what is n here? N is 5. So it means that n is 5. So an minus 1 has the highest weight and an minus 1 is the lowest weight. And this representation is called as which representation? The decimal representation, which is understandable by human. Got it? Now, we have another representation, binary representation. We call this as the base 2. There are only 2 possible digits, 0 or 1. So 1, 2, 3, 4, 5, 6. What is n? N is 6. This is A5, A4, A3, A2, A1, and A0, and this is what? The base. It has the highest weight and it has the lowest weight. Got it? There are 2 possible values. And octal, there are different possible values. We say, example, 5, 7, 3, 4, 5. What are the digits which are possible in octal? From 0 to 7. So if we say 9, 9 is not allowed in octal. Okay? And now hexadecimal. Each symbol can have 16 possible values between 0 and 9 and A to F. How many digits it has? How many digits? 1, 2, 3. Sorry, it's 16. Please change it. Okay, it's 16. 1, 2, 3, 4, 5, 6. What is n? N is 6. This is A5, A4, A3, A2. What is base? It's 16. Not 2, it's 16. Sorry, this is a small mistake. Okay, so now this is 16. So hexadecimal are used to represent binary in a more compact form. We'll study it later on next slide. Now we call this is the weighted position. So now we have a decimal number system which consists of 0 to 9 and it is understandable by human and position is important. So if we say 7594, 7 has the highest weight. What is its weight? 10 to the power 3. What is the weight of 5? 10 to the power 2. Okay, now if you take it, so now we have this number. Can you see here? 7, 5, 9, 4, which is actually 10. This is A3, A2, A1, and A0. So this has a weight of 10 to the power 0 it has a weight of what? For 1 and 10 raised to the power 2 and then 10 raised to the power 3. You multiply this with the weight. 7 multiplied by 10 raised to the power 3, 7,000. So it is 7,000 plus 5 multiplied by 10 raised to the power 2 plus 500 plus 9 multiplied by 10 raised to the power 1, 90 plus 4 multiplied by 10 raised to the power 0 is 1, and it is actually 7594. Got it? Okay, so now we have a weight. So this is called is the most significant digit, and it's called as the least significant digit. So n minus 1 is the most significant digit, and the other one is the. So the value of each symbol is dependent on its time and its position in the number. In general, so it is an minus 1, n minus 2 up to a0, 10. So it means an minus 1 multiplied by 10, n minus 1. Then this is the generalized formula, and this is the specific. What is n here? What is n here? N is 4. N is fair. So this is A3, A2, A1, and A0. Got it? Good. So in the numbers, an minus 1 constant indivisible, n is the highest weight and the lowest weight. So now we also have different numbers. That is 2, 3 divided by 4, 2.75. So can you see here 2 multiplied by 10 to the power 0? Then 7 multiplied. Okay, now we will explain this with an example. So in general, so now we have two parts. In the previous example, we didn't have the fractional part, but now we have the decimal part and the fractional part. So this 2 is the whole part, and this is the fractional part. So how can we represent it? So it was an minus 1, an minus 2, blah 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 up to f1, f2, and I will explain this with an example because example is always good. So I will rub it off. So can you see here? So let's assume now we are using some other numbers. Let's assume this is 7, 4, 5, 3 point. I'm using different pen color. 6, 4, 2, and this assume we have this 10, the base of 10. Okay, now we have two things. N is 4, which represent the whole part, and now M is 3, which represent the fractional part. So how can we represent it? So actually it is A3, A2, A1, and A0, and this one, sorry, I can use different pen. So this is an A3, A2, A1, and A0, and this one F1, F2, and then F3. So in this case, this is M. So actually, its weight is 10 to the power minus 1, then minus 2, 10 to the power minus 3, and this one is 10 to the power 0, then 10 to the power 1, and 10 to the power 2, and then 10 to the power 3, and go on until we go to 10 to the power n minus 1. Got it? Any question? Should we proceed? Yes, good. So now if you say, so now we have the radix or the base of the number system is the total number of digits allowed in the system. So in the base 10, we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 10 digits. That is also called as the base of 10. So for the decimal number, the base is 10. Okay, now we have the weights are in the power of 10. Okay, to relate to decimal system. So now the same thing, minus 1, minus 2, and minus 3. This represent the fractional part or the whole part? Fractional part. And this will represent the whole part. So these are n numbers. So we will go into 10 to the power n minus 1 and sorry 10 to the power n minus 1. Okay, and here 10 to the power minus m if there are m digits. Got it? So if you look at here, now we have this number. How many digits in the whole part? 2 digits. Sorry, 3. Yes, 5 multiplied by 10 is what? 500 plus 90 plus 3. Okay, 0.6, 0.08. And we do this. So this is the symbol. Okay, this is not 30. This is 3. You can change it, please. It's 3. Okay, and when we convert this, this is 5934. What is n here? What is n here? 3. What is m here? Okay, now binary numbers. So there are two representation on and off. We already studied it. Okay, now If we want to represent more information, because a binary digit can be used to represent only two discrete values, but if we want to represent more discrete values, we need more bits. So if we increase the number of bits, how many bits are we have? 2 bits. So if we discrete the number of bits, so what are different possible combination? 0 0, 0 1, 1 0, and 1 1. If we have 3 bits, 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Got it? So now if we want to have, okay, now we can represent something. So now we have two bulbs. Let's assume we have two bulbs. This is bulb 1 and bulb 2. Both are off. We say, okay, autumn. 0 1, spring. 1 0, summer. And then 1 1, winter. How many information values can we have? 4. How many bits? 2 bits. Got it? So this can be these 2 bits. So these 2 bits can give us 4 information. So if we increase the number of bits, we can represent more information by increasing the number of bits. So in general, n bits can be represented by 2 to the power n different states. For m values, log 2m. I will explain this with an example. Okay, so 1 bit. How many values? 2 values. 2 bits, 4. 3 bits, 8. 4 bits, 5 bits, 32. 6 bits, 7 bits, 128. 8 bits, 256. 9 bits, 512. 10 bits, 1024. 11 bits, 2048. 12 bits, 4096. 13 bits, 8192. 14 bits, 16384. 15 bits, 32768. 16 bits, 65536. You need to memorize this. Just like I'm saying, you know, most of the students are there. So now these are all the values. So the possible values. 4 bits. How many possible values? 16. 32 values. How many bits? 5. Got it? Okay. Now, if we want to represent any number, so then we can okay. If we want to represent 37, how many bits are required? 6. Because 2 to the power 5 is what? 32, and 2 to the power 6 is what? 64, and it lies within this range. So how many bits are required? 6 bits are required to represent 37. If you want to represent 140, 2 to the power 7 is what? 128. 2 to the power 8 is what? 256. It lies within the range of 128, and how many bits are required? 8. So this is the minimum number of bits required to represent some information. It depends on the value. So the larger value means what? More bits, and the lesser value, less number of bits. Got it? Okay. So now this is a table. This is the counting in binary. Okay. How do we reach to, and so okay. So now I will send this with an example, and this example. Okay. Now this is a 4-bit system. How many values can we represent? 16. 16. But index always start from 0. So it can represent from 0 to 15. If we have 5 bits, from 0 to what? 5 bits. 0 to 31. 6 bits. 0 to 63. Okay. How can we compute it? So let's assume we have some weights. So we call this as weight 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. What is n here? N is 4. In general, we can start from 2 to the power n minus 1, 2 to the power n minus 2, blah blah blah, until what? 2 to the power 0. What is its weight? 1, 2, 4, and 8. Okay. Now let's assume if we say 1 0 0 1. So what we are adding? 8 plus 1. What is 8 plus 1? 9. Okay, now 0 1 1 0. What I'm adding? 4 plus 2, 6. 1 1 1 1. Okay, 0 0 1 0. So now these are the tables, and you can see table. Okay, so now if you look at here, 1101, 8 plus 4, 12 plus 1, 13. Got it? So how we transform a decimal value into a binary number? This is the formula. Any question? Should we proceed? Easy? Fast or slow? Fast? Okay. Okay. No, but you got the idea or not? You got the idea, then it's good. It's already recorded. You can do it really slowly on the recording. Okay. So now, if you look at here, now we have an exponent. 1 bit. How many information? 2, 3, 8, 4, 16. I counted it until here. 2 for 16 is 65,536. So now this was the table. Okay. So, okay, now if we want to represent, okay, now look at the table. If you want to represent 600, how many bits are required? 600. Look at the table. 10. If you want to represent 20,000, 15. Okay, 80,000, 17. So now this is the way how do you calculate it. Okay. So now this is the power of n. Okay. Now binary values, where it's in the power of 2, 0 and 1. Octal, power of 8. What are the allowed digits? 0 to 7. Hexadecimal, 0 to 9. There are 16 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, 11, 12, 13, 14, and 15. What is the code for A? 10, 11, 12, 13, 14, and 15. How many digits are allowed? 16. Base R. This is the weight in the power of R. Now, in the binary, how many allowed digits are there? 2. Octal, 8. Decimal, 10. Hexadecimal, 16. Okay. Now, if you start counting, okay, now, just you know this decimal, you start from 9, it's high school, 1011 and until simple. Okay, how do we do? Okay, forget about binary. Now look at the octal. 0001. When we reach 7, there is no 8 in octal. Then we do what? 10, 11, 12, 13, 14, 15, 16, 17. After 17, there is no 18. Then 20. Then 21, 22, 23, 24, 25, 26, 27. Then 30. 31, 32 until 37. Then 40. Blah blah. Got it? For hexadecimal digits, the counting. Now we 9. Then we do not go to 10. Then A, B, C, D, E, F. Then 10. 1, 1, 1, 2 until 1, 9. Then 1A, 1B, 1C, 1D, 1E, 1F. After that, 20. 2, 1, 2, 2, then 2, 9. Then 2A, 2B, 2C, 2D, 2E, 2F. After that, 30. This is the count. You got this hexadecimal. You got the octal. And binary, I told you that, how do you calculate it? The method that I told you. Okay, so now, if you look at here, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4. 2 to the power 4 is what? 16. And 16 is actually. Got it? Okay, now, 8 plus 4, 12 plus 2, 14 plus 1, 15. Got it? So simple, and you say, you're more intelligent than me. I'm an old guy. So now we have the base R to decimal conversion. So now if you look at here, now base R, base can be anything. It can be 2, it can be 8, or it can be 16. Now we want to convert it into decimal. Okay, now if you look at the whole part, what is this? N. What is this? M. N is 4, M is 3. Okay, so now we start from 2 to the power 3 because A n minus 1. 2 to the power 2, 2 to the power 0, 2 to the power minus 1, and 1. Okay, why we skipped some zeros? Can you see? We have 2 to the power 3 and then 2 to the power 2. Where is 2 to the power 1? Because the third digit is 0. And anything multiplied by 0 is 0. Got it? So okay, can you see here? Now, if you look at here, so now this is actually, I'm using different pen. 1, 1, what? 0, 1, dot. Then 1, 0, 1. Its weight is 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. And now its weight is 2 to the power minus 1, 2 to the power minus 2, and 2 to the power minus. If we calculate it, so actually this is 8, this is 4, this is 2, and this is 1, and this is 2 to the power minus 1, 1 divided by 2, 0.5, 1 divided by 4, 0.25, and 1 divided by 8, 0.125. Okay, now 1, what is its weight? 8 plus what? 4. Okay, now we skip 2 to the power 1. Can you see 2 to the power 1 is not here? Why? Because 0. So we skip it. Plus 0 plus then 1 dot. Now 1, what is its weight? 0.5 plus 0 plus 0.125. So if you see it, 8 plus 4 plus 1. What is this? 13 dot what? Got it? Proceed. Okay, the same thing. It's very simple. Now instead of, now we have 572. It has a weight of 2 to the power 3. Now it has a weight of what? 8 power 2. Then 8 to the power 1, 8 to the power 0, and 8 to the power minus. Same thing. Now, and then you can just compute it. 8 multiplied by 8 is what? 64. 64 multiplied by 5, 320. And then 7 multiplied by 8, 56. And then you can compute it, and that's this. How do you convert it? Now, the second base is, the first base is 2. The second base is what? 8. The third base is what? 16. Got it? And now this is the base 5. Okay, so the base 5. Okay, now we will write some general formula. In this case, okay, so I will write it like this. And please look at here, because if you remember this formula, so the general formula is this. Okay, now we have some digits, n minus 1, n minus 2, blah blah blah, then a 0. Okay, so now dot. What is n here? It is n. Okay, dot. Now we have the fractional part. The fractional part is f1, f2, fm. Got it? Now we have a base of r. What are the possible values of r? It's 2 in the first case, then 8 in the second case, and 16 in the third case. We are not interested in base 5, but just for the sake of completeness, I did it. Okay, how can we compute it? Okay, now we take the first digit. What is the first digit? an minus 1 multiply by, okay, we divide it into 2 to the power 3. Instead of 2 to the power 3, what should we do? R n minus 1. Got it? an minus 1 dot r n minus 1. Then please help me out, please. an minus 2 r what? n minus 2 plus blah 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 plus a0 dot what? r0. This is the decimal part or the whole part? Whole part. And then about the second part, then we need f1. f1 multiplied by what? Can you see? R minus 1 plus what? f2 what? Minus 2, and blah blah blah. We go until what? fn. So this is a generalized formula, and this is a specific values of different things. Got it? So now, if it's in this example, what is this? A2, A1, A0. This one is F1, F2, and what is this? R. R. An minus 2, An minus 1, sorry, N minus 2, A2, which N is 3, so A2, A1, and then A0. Simple. Got it or not got it? So the thing is, whenever you want to solve some problem, so you need to, this is a generalized expression and these are different. You just put in some values. Any question? Should we proceed? Understood? So far so good? Good. Okay, now these are the tasks. So you please go through home and please do these tasks by yourself. Okay, now we want to convert a decimal number to a binary. So there are two different methods, but first method is the sum of the weight methods, and the other method is repeated division by 2. Okay, now this is the sum of the weight methods. Now we want to convert 9. Should I rub this off? Everything is clear? I think so. I'm also recording the lecture, so you can also see in the thing. So if we say, if we say 9, we want to convert it into binary. So we have some weights. Please remember these weights. So this is 1, 2, and these are all power of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 112, 1024. Okay, these are all of the weights. How can I divide 9 into a sum of some of these? How can I divide 9? 8 plus 1. Got it? Okay, now we have different weights. This is 1 to the power 0, to the power 1, to the power 2, to the power 3, to the power 4, to the power 5, to the power 6. This is 1, 2, 4, 8, 16, 32, 64, to the power 7, which is 128. Got it? Now if I want to find the binary of 9, how can I get 9? 8 plus 1. So in the 8, there will be 1, and plus 1, it will be 9, and the rest are all zeros. Any question? Okay, now we got 18. How can we divide 18? 16 plus 2. So 16, 1, and got it? Then what about 58? 32, 1, then 16, 1, then 8, 1, then 2, 1. Am I right or not? Got it? 0.625. Okay, now this is the decimal fraction. 0.625. So we have, okay, so for the other thing, we will have, for the fractional part, 2 to the power minus 1, and then 2 to the power minus 2, and then 2 to the power minus 3. 2 to the power minus 1 is equal to what? 0.5, then 0.25, then 0.125. Okay, so I want to divide this 0.625, so I can write it 0.5 plus what? Plus 1. 0.5 is 1. 0.5 is 1, and 0.125 is 1. So what is the code? 0.101. Got it? So this method is called as what method? Sum of the weight method. And the weight we studied. So what is the weight of an minus 1? What is the weight of an minus 1? An minus 1. It is actually, what is its weight? 2 to the power n minus 1. What is the weight of an minus 2? 2 to the power n minus 2. What is the weight of f1? 2 to the power minus 1. So what is the weight of fi? 2 to the power minus I. So now we have, sorry, if you look at here, so we can generally, we can say we can have different digits. We can have different digits, and that digits can be, so you can say an minus 1, an minus 2, blah 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 until a0 dot f1, f2, blah 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 up to fm. Remember that thing? So we can say, okay, now we can have any a, so I can have any value between 0 to n minus 1. So I is belong to a set for n minus 1, n minus 2, blah, 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 until 0. So what is the weight of AI? The weight of AI is actually 2 raised for I. So the weight of n minus 1 is 2 raised for n minus 1. What is the weight of Fj? 2 raised for minus j. So for the fractional part, it's minus, and for the whole part, it's plus. Got it? Any question? So I have generalized it. So now we have generalized it. Okay. So now it's a simple thing for 58. So get 58. We 32 plus 16 plus 8 is 50, and plus 2 is 58. And this is the same thing. 18 is 16 plus what? 2. Got it? And now we go for the fractional part. So for the fractional part, can you see 0.625? How can we reach 0.5 plus 0.125? So this one is 0.625. And for what? The second thing, 0.75. So how can we get 0.75? 0.5 plus 0.25. So 0.5 plus 1. So this is 0.11. Got it? Should we proceed? Okay. Now this is also a very simple thing, which is called as the repeated division by method. How can we convert it? So it's a very simple example. Okay, now we did. Okay, now if you look at here, can you see here? What is this value? 1001, 9. What was this value? Remember, 16 plus 2, 18. What was the third number? 58. Remember? Okay, now we want to solve the same problem using different method. We call this as repeated division by 2. It's very simple, and you will really like it. Okay, now if we say we want to convert 9, okay, so how do we do it? 9. We divided it by 2. 2 4s are 8. Remainder is what? 1. Then 2 2s are 4. What is remainder? 0. 2 1s are 0. What is remainder? And then we go from this direction to this direction. So the code is 1001. 100. Got it? Now we want to convert 18. 18 is not. Then we can go for 58. 58. 2. Okay. 29. Then 0. Then what? 14. Then 1. Then 2 what? 7. 0. Then 3. 1. 2. 1 1. So the code is what? 1 1 1 1 1 1 0 1 0 1 1 1 0 1. Okay. So these are two different methods. Okay, so in the first method it was the sum of the weight method, and the second method is repeated division by 2. So if you look at here, so now can you see here? Now this is another example, 43. So 2, 41, remainder is 1. So this is the MSB. So now it's any question? Should we proceed? Okay, now repeated multiplication by two method. That's okay. Now we have two parts. One is the decimal part. You have some question, please ask me. Everything's clear? Good. Okay. Now if we have repeated multiplication by 2 method, it's for the fractional part. So to convert a decimal fractional into binary, so now we have two parts. One is the whole part, and then is the fractional part. So if we have a fractional part, so we have repeated multiplication by 2 is used. Okay, now I'll explain this with an example. Okay, now we want to convert 0.3125. How does it convert into this? Okay, now should I rub this off? Okay, it's very simple, it's not difficult, but this is a different method. So how do we do it? So can you see here? Okay, now you multiply everything with 2. So 0.315 multiplied by 2. What is the result? 0.625. We only consider the fractional part. We take this fractional part, 0.625, and then again multiply by 2. What's the result? 1.25. Then we again take the fractional part or the whole part? Fractional part. What is fractional part? 0.25 multiplied by 2 is what? 0.50. And then 0.50 multiplied by 2 is what? 1. So what is the coding? And you go from here to here. This is the MSB and this is the MSB. So can you see the red? 0, 1, 0. This is the way how you convert it. Got it? So what do? You multiply each fractional part with 2 and then take the decimal, the fractional part again, and then you again multiply it by 2. Then again take the fractional part and then again multiply by 2. And if you look at here, if you look at the pattern, so in the first step, the fractional part has a bigger number, 0.625. Then it becomes what? Less. It's 0.25. Then it becomes less. 0.5. Okay, now it's 1.25, then it's 0.5, and then 0.02. So actually, it will be converted into 0, 1, 0, and 1. So this method is called as, for the repeated multiplication by 2 method. It's for the fractional part or for the whole part? For a fractional part. So we have different methods for the whole part, which is repeated division by 2, and for the fractional part, which is repeated multiplication by 2. Got it? Okay, now, if we want to convert 46 as an integral part, so now we have different methods. So 46 divided by 2, 23. What is the remainder? 0. So we are reading it in reverse order. 1, 0, 1, 1, 1, 0. So this is the equivalent of 46. Okay. How can we divide 46? We also have the repeated the sum of the weight methods. 46. How can we divide? 32 plus what? Plus 16. 32 plus 16 is 48. No. Then plus 8. 40 plus 4 plus 2, and then we can do that. So 2, 1, 1, 2, then can you see here? So the 46 is 1, 1. Got it? Okay. So now in 46, so what is the code? What is the code for 46? So reading, so 1, 0, 1, 1, 1, 0. So this is 1, 2, 4, 8, 16, and 32. So 32 plus 8, 10 plus 4 and plus 2, which is actually 46. So this is repeated division by 2 method. So now we have converted the decimal part or the whole part? Whole part. And what about the decimal part? So 0.6875 multiplied by 2. We take the fraction. What is the fraction? 0.3752. Again multiply by 2. Fractional part. Again multiply by 2. Fractional part. Again multiply by 2. Again it becomes 0. So then we do it in the forward order. So this is 1, 0, 1, 1. Got it? Any question? Should we proceed? Okay. Now we have the base R to decimal, and then the decimal to binary base 2 and decimal R2. So we can have this method. Okay. Now we want to convert a decimal to an octal number. We also have the repeated division by thing. So now, how can we divide this? The same thing. We want to convert 99 into base 8. In the previous example, we divided it by 2. But when we want to convert into octal, we will divide it by what? 8. So we will divide by 8. So 12 multiplied by 8 is 96. What is the remainder? 3. Okay. 8. 8 multiplied by 1 is 1. What is the remainder? 4. We do it in this order. So this is 1, 4, 3. Okay, now it is 1, 4, 3. Okay, now please remember, it has a weight of, can you see here? It has a weight of 8 raised to the power 0. It has a weight of 8 raised to the power 1. It has a weight of 8 raised to the power 2. What is its weight? 1. What is its weight? 8. What is its weight? 64. Okay, now you multiply. So you can say 64 multiplied by 1 plus 8 multiplied by 4 plus 1 multiplied by 3. 64 multiplied by 1 is what? 64 plus 32 plus 3. So now we converted decimal into octal, and then we convert back. So whenever I give you some questions, so you can also do the cross check. You can also do cross check. Got it? Any question? Got it? Should we proceed? So now if you look at here, so now we have this 99, 12, remainder is 3, so 1, 4, 3. Now to hexadecimal? It's very simple. To convert a decimal into octal, so hexadecimal. So please replace this to hexadecimal. So we use successive division by what? 16. Okay. Now let's assume if we have 1, 2, 3, 4. Should I rub this off? Good. Now what's the thing? 1, 2, 3, 4. If you want to convert it to hexadecimal, so we should divide it by what? 16. So we will divide it by 16. Okay. So now we can do 1, 2, 3, 4 divided by 16. So 16 sevens are 1, 1, 12. 1, 1, 12. The remainder is 1, 1, and 4. Okay. And then we again multiply by 16, multiply by 7 is 1, 1, 12. What is the remainder? 2. What is the quotient? 77. 77 is the quotient. And what is the remainder? 2. Again divided by 16. So 16 4s are 64, 16 5s are 80. Okay, so we say 16 4s are 64. We subtract 64 from 77. What is the remainder? 13. Got it? Okay, now we have this code A, B, C, D, E, and F. What is the code for A? 10, 11, 12, 13, 14, and 15. What is the code for 13? D. So what is the answer? 4D2. Now we have, okay, now we have 4D2. So now we have converted this decimal number into hexadecimal. Now we want to convert back. So we want to convert back. This is actually 4D and 3, which is actually 16. But we want to convert back into decimal. So what we can do? Okay, now this, please remember, what will be now the weight? 16 for 0, 10, and then part 2. Okay, 16 for 0 is 1, 16 is 16, and 16 multiplied by 16 is 256. Got it? Okay, now we have 256. So you can say 4 multiplied by 256, because we have 4 multiplied by 256, plus D. What is D? 13. 13 multiplied by what? 16, plus 3 multiplied by 1, and 256 multiplied by 4. 256 multiplied by 2 is 512 and 1024. So this is 1024. 1024 plus 13 multiplied by 16. 208 plus 3. So you say 1024, 208, and plus 3. Which one? Which one? Oh, 4D2. So 2. 2 multiplied by 1. Yes, you're right. 2. So now we add 2. Got it? So what did we do? We converted this. What is this? Which number? Decimal or hexadecimal? Decimal. We converted this decimal into hexadecimal by repeated division by 16, and then we got 4D2, and then we apply the sum of the weight method to convert back this into decimal. So now these are the tricks. These are the tricks that I'm telling you, because if I want you to convert it into a decimal into hexadecimal, so you can convert it into hexadecimal and then convert it back. Then you can see that whether your answer is right or not. Did I use calculator here? And you know, all of the new generation, I will call it Z generation, they are very much addicted of the computer, and the use of the tools or something like that. So if you try these things by hand, this is my advice to you. If you're trying all these things by your hand, it will help you a lot. It will help you a lot. Okay, so now we have this thing, and then we convert it back into binary. And this is very simple. This is very simple. This is one of the easiest method that we have. Okay, now we have Should I rub this off? Okay, so now. Okay, now we have, can you see in the octal, in octal we have different 8 digits. So it range from 0 to 7. So it may say 0, 1, 2, 3, 4, 5, 6, 7. Okay, and each has a binary representation. It is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So now these are the codes. Okay, and then you just write these codes. Okay, okay. Now, if you want to convert this number, what is this number? In which base? Binary. Which base? Octal. So you just divide this into a partition of 3 bits. And starting from here, if I'm from here, from the right, so if you're seeing from here, so from left to right, and from here from right to left. So we start from the MSB. We group this into a group of 3 bits. Can you see the black? How many bits are there? 3. Can you see the blue one? 3 bits. And can you see the red one? 3 bits. And the left is 1. Okay, this is only 1 bit. Okay, so now what is the, can you see here 111? Can you see here 111? 111 is the code for what? 7. This one is 7, then 2, then 3. You need to remember. Please remember it, and please try this. If you remember, it will make your life easy. And 1. And I can tell you, I can give you any number, and then you say 1, 3, 2, 7. Got it? So it's more simple. Okay, now for hexadecimal. So for the octal representation, we need 3 bits. For hexadecimal, how many bits? 4. So we divide it into a pack of 4 bits. So if you look at the black thingy, how many bits? 4. Blue, 4. So okay, this is F, this is 5, this is A, this is 3. And now if we have, we can extend it to then 8, 9, A, B, C, D, E, and F. So now we have 0, 0, 0, 0, 0, because we need 4 bits. Then you can say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, then 1, 1, 1, 1, 1, 1, 1, 1. Okay, so now if you look at here, F has a code of 1, 1, 1, 1. Got it? And then 5, 0, 1, 0, 1. And then A, 1, 0, 1, 0. But A is equivalent of what? 10. And 10 is what? 8 plus 2. It has a 1, 2, 4, 8. Okay, now 1, 2, 4 and 8. 8 plus 4, 12 plus 2, 14 plus 1, 15, which is equivalent to F. Got it? Any question? Should we proceed? Good. Okay, now, so this is very simple. And this one is the simplest way. Can you see the color coding? The color coding. So 2, 2, 2, 7, 3, 1, 5, 6. Then 2, the same thing. Okay, now hexadecimal. 8, I'm not looking at this. B, 9, 1, 1, 0, 0, C. D, sorry. And then the same thing. Got it? So you can go through all these codes. 1, 0, 0 is 8. Okay, and then this is B. This is 1, 0, 0, 1 is 9. 1, 1, 0, 1 is D, and then got it? So now you have the code. Any question regarding this? Okay, so you can do a lot of things. You can do a lot of things. So I can explain this with this example. So now what is a bit? A binary digit that can have a 0 or a 1. Nibble is a 4-bit data. So now if you look at here, so this is the binary representation, decimal, hexadecimal, and octal representation. Okay, and now if you want to, if you have an 8-bit data, so can you see here 1010 red stand for A, 0001 green 1. 6D color coding 16 bits. Then F230, the code for F, the code for 230. 32 bits, all these 3 C02DF. Okay, now we have, if you have kilobytes, it can store 2 to 10 bytes. Megabytes. How many bytes? Mega. 2 to the power 20. Giga. 2 to the power 30. Tera. 2 to the power 40. These are the values. So okay, now these are the numbers. You can go through all these the numbers. So now binary is also the flexibility of representation. We also have different information type which has numeric type, which is actually some numbers. So in C++ you may have studied different data types like int, float, double, long, and double. So all information can be represented in the form of numbers, and they have different representation. So we have different type of numeric data. Okay, and then the non-numeric data like the ASCII character. The ASCII character A is some code. What is the code for A? 65. What is the code for B? 66. C 67. Small a 97. Small b 98. So this is non-numeric data. Okay. What about colors? In the next example, what about colors? Numeric or non-numeric? Colors. Non-numeric. Colors not, but we convert it into numeric representation. So what is the code for red in this particular example? 0. What is the code for orange? 1. So this is a non-numeric data. Okay, now what we will do. So okay, so I will ask every student, please have your page and pen, and I will give you some tasks, and I will help you. This is not an evaluation, just like to help you. Please some task. Okay, so now and you will do all the you will solve. So now this lecture is finished. Okay, so now I am stopping the recording. You can go through all these lectures